Everyone, good morning. So let us derive the differential equations of equilibrium in a 3D stress system. We are going to derive differential equations of equilibrium in a three-dimensional stress system. Okay. So, to begin with, let us first consider a three-dimensional system. This is the three-dimensional coordinate axis. Let this be x, y, z. Now, on this, I am going to draw a parallel pipette. Parallel pipette has been drawn. Let the vertices be A, B, C, D, E, F, G, H. Alright. So we have considered an infinitesimal element in the form of a parallelepiped with its face. These face are parallel to the coordinate planes. We have considered a Cartesian coordinate system. This derivation is in Cartesian coordinate system. Okay, so let us consider an infinitesimal element to be isolated from the body, and it surrounds the point P. All right, let the dimensions of the parallelepiped be dx, this is dy, and then this is dz. Alright, we have the dimensions of the parallelepiped. Now, for any body to be in equilibrium, it should continue to stay in its state of rest or of uniform motion. Yes, so here we have considered the parallelepiped to be in equilibrium and it is going to be at rest. If the parallelepiped is in equilibrium and at rest, then the inertia forces are absent. Alright, so let us start with respect to the normal stresses. Now, let us consider the face EFGH. This lies in the ZY plane. So, for face EFGH, okay, the normal stress is represented by sigma x. Now, the face in front of it, that is ABCD. ABCD. For this particular face, the stress is going to be sigma x plus sigma x because it is for EFGH, plus you have an increment. Say, let us say the increment to be delta sigma x. And if this is positive, this is going to be negative, or if this is negative, this is going to be positive. These two are going to be opposite in signs. Next, how are we going to calculate this increment delta sigma x? So, if you have an increment of stress, say increment of stress, that is sigma x, and that is by a unit length. All right, we're just going to consider with respect to a unit length, then it is dou sigma x divided by dou x, but here the length is delta x. Okay, so here the length is dx, sorry, it is dx. Therefore, this increment stress delta sigma x, this is nothing but dou sigma x by dou x into dx. All right, so therefore now the normal stress for face ABCD can be written as, say, sigma x dash. This is nothing but sigma x plus delta sigma x, that is nothing but dou sigma x by dou x into dx. Similarly, if I consider the face CDH, I've considered C, D, H, G. On the face of B, A, E, F, for this particular face of X and Z, it is going to be sigma Y. Okay, so for face A, B, E, F, it is going to be sigma Y. For C, D, H, G, sigma Y, let us call it as sigma Y dash. That is nothing but sigma Y plus dou sigma Y by rho Y into dy. Alright. Similarly, for face BCGH, that is the top face, BCGH. We are going to have sigma Z dash. Bottom faces AEHD. AEHD is nothing but sigma Z. So BCGH is sigma Z dash, that is sigma Z plus dou sigma Z by dou Z into dz. If at all you get confused on which face you're going to get which normal stress, then I have a small technique. That is, let us start off from here. E, F, G, H. The plane is Z and Y on which it lies. So take the other one that is left out. That is the X component. So sigma X. Then the front face A, B, C, D. So it is right in front of it. Definitely there has to be an increment with respect to the same normal stress. So it is sigma X plus delta sigma X. Now coming to this A, B, C, D. A, B, we have just written the increment. So A, B, C, D is sigma X dash plus sigma X dash, that is equal to sigma X plus the increment, that is dou sigma X by dou X into Tx. Next, C, D, H, G. Just look at the plane before it. That is nothing but A, B, E, F, A, B, F, E. So A, B, E, F or A, B, F, E. This lies in Y and Z plane. The left out component is Y. The coordinate left out is Y. So definitely it is sigma Y. Next, A, E, H, D, the bottom one. It lies in X and Y plane. Definitely the normal stress. Normal means perpendicular, alright. So a perpendicular has to be drawn. I'll just show you. So this is A, E, D, H. It lies in Y and X plane. What we call these as normal stress. Normal means perpendicular. So this has to be sigma Z. The axis that is going to be perpendicular to X and Y, that is Z. So it comes out of it. It's a normal drawn to it. It's perpendicular to it. That is how the faces have these respective normal stresses. Alright. So let us move forward. Now, let us talk with respect to the shear stresses. Till now, we have spoken the normal stress. So, for these phases itself, I'll talk about the shear stress. Alright, this is the normal stress. So, for A, B, C, D, I'll just write it here as normal. For the same phase A, B, C, D, the shear stress is going to be A, B, C, D. Okay. For this A, B, C, D, the normal stress is going to be tau xy dash. That is nothing but tau xy plus dou times tau xy by dou x into dx. We are writing with respect to x. Hence, you can see the denominator is dou x and then here it is multiplied with dx. Now, for CDHG, the shear stress is tau yz dash. That is nothing but tau yz plus dou tau yz divided by, it is with respect to y, so it is dou y multiplied by the dimension dy. Last, BCGH. For this, it is tau zx dash. That is nothing but tau zx plus dou tau zx by multiplied with it is with respect to your sigma z, so it is multiplied by dz and the denominator is dou z. Alright, so these are the shear stresses for the respective phases. Alright, so once we write down the shear stresses, in order to check for the equilibrium, if you remember in your elements of mechanics, we had equilibrium conditions. Summation fx equals 0, summation fy equals 0, summation fz equals 0. Okay, z because we are dealing with three coordinate axis. Else we would have just stopped at x and y. Now we have three coordinate axis. Summation fx, summation fy, summation fz. All the three have to be 0. Then if these three have to be 0 means, so if I want to put it in terms of statement, I can tell for the parallelepiped to be in equilibrium, it should satisfy two conditions. That is, sum of forces in each direction. Sum of forces in each direction must be 0, and then sum of moments. If you consider the moments, then sum of moments of forces about the three reference axes. Say if you're going to consider with respect to y or z, x or z. So sum of moments of forces about the three reference axes have to be 0. Now I will be considering only the first one, that is summation fx is equal to 0. What are the forces that are going to be there along the x direction? First, it is going to be sigma x plus dou sigma x by dou x into dx. This one is going to be there, and then minus dou sigma x. We are going to have this one, and then we are going to have tau xy and tau yx both. So we will be having this, and then we are going to have tau zx also. So all the x components are going to be considered. First, let us try to arrange these forces of normal and shear stress. Okay, both the normal stress and shear stress in your parallelepiped. Once you write it in your parallelepiped, then it is going to be very easy for you to take up the equilibrium condition, that is summation fx is equal to 0. I'll redraw it by including the stresses, so it becomes easy for you to understand. So this is the y-axis. I'm just redrawing the same diagram, x and then z. Okay, parallelepiped is drawn. Let us name the vertices A, B, C, D, E, F, G, and H. Alright, so let us start with the top face first. So the bottom face is sigma z. Okay, so top face is going to be sigma z dash. For convenience, let us take this to be the positive one. So this is sigma z dash. So the bottom face is going to be sigma z. So let us take the positive direction for the shear stresses also. This is going to be tau. We are writing with respect to z. Z, it is parallel to y. Y, tau z, y, tau z, y dash, and then tau. We are writing with respect to z parallel to x, tau zx dash. Similarly, this has to be in the negative direction, tau zy, only tau zy. Okay, and then this has to be in the negative direction, tau zx. Now here you can understand why I have written tau zx dash or tau zy dash. This is because of the increment value that has been added. Here it is just the normal value. Here we are not adding any increment. The increment is because of the height. Can you see A, E, D, H lies on XY plane, whereas the top face, that is B, F, G, C, is at a height of del dz. This dz, the dimension. Okay, it's at a height of dz from your xy plane, hence the increment. Okay, now let us draw the stresses for the other faces. Let us consider the front face A, B, C, D. For the front face, let me draw it over here. The force that is going to be normal is sigma x dash, and then the shear forces are going to be tau xz dash, and here it is going to be tau xy dash. So how have I written? I am writing with respect to A, B, C, D, which is in front of E, F, G, H. So this face E, F, G, H lies on Y and Z plane. Okay, it lies on Y and Z plane. So first, the negative, that is normal stress of sigma x. The left out component is x. So for the front face, it has to be positive. So I'm going to take it along the positive x direction. And then I'm going to draw the shear force for the other two planes. So if for this particular shear force along x direction, so x, and I'm writing parallel to z, so z. Then for this one, I'm writing with respect to x axis, so x parallel to y, y. So let us just write the negative directions for this. So this is going to be tau x z dash here. So this is tau x z, and then this is tau xy dash, so this is tau xy. Okay, we have written for the front, top and bottom faces, front and behind faces. Now we have to just write for the side faces. So your A, B, F, E, this face lies in x and z plane, hence negative, because we are taking for convenience that the faces that rise on the plane, exactly on the plane, is going to be negative. The left out component is y, so this is sigma y. Okay, so on this face, positive sigma y dash increment, please do not forget. And then shear forces, so this is with respect to y, y parallel to z, z dash. Then with respect to y, parallel to x dash. So here bottom opposite to this, so tau yz. Then here along the negative x direction, tau yx dash. So here it is tau yx. Yes, we have written all the forces, all the stresses, we have represented them in the parallelepiped. Now we will be considering summation fx equals 0. Yes. So let us take down all the forces in the x direction. So x is this, we have this, we have this, we have this. I'm just marking it up so that it is going to be easy for you to consider it. Okay, and this. Can you see? So let us start from the behind face. The behind face, that is E, F, G, H. On that particular face, we have minus sigma x. On the front face, A, B, C, D, we have sigma x dash. Then bottom face A, E, H, D, we have tau zx. Then top face B, F, G, C. This is C. B, F, G, C. We are going to have tau zx dash. Then the side faces A, B, F, E. I have tau yx. Then D, C, G, H. I have tau y dash, tau yx dash. Okay, how are we going to write it? First, let me write them down. Sigma x dash, then tau zx dash, then tau zx, tau yx dash, and then tau yx. These are the components considered for summation fx equals 0. We know the values of tau x dash, tau zx dash, tau yx dash. Yes, we have taken with respect to the increment values. So I'm going to replace with them with respect to the increment values. And then on top of it, I'm going to consider something called as body forces. In the very beginning, we spoke about the surface forces and body forces. So the body forces are going to be X, Y, and Z. Capital X, capital Y, capital Z for the respective coordinate axis. Okay, let me write it in form of an equation. Let us solve that so that we are going to arrive at the end. So first I'm going to write sigma x dash. So sigma x plus it is dou sigma x by dou x into dx. This is the value of sigma x dash. And what are the other two components? I'll teach you a simple method so that you can remember. So we have written dx. The other two components are dy and dz. Next, it is sigma x. Okay, so it is in the negative direction, so I've written minus. These two components have to be written, so dy dz for this. Next, let us write tau yx dash. So it is tau yx plus dou tau yx by dou y into dy into, we have y, dy written, the other two components are dx and dz minus, this is positive, I'm going to write just tau yx. What are the two components written? dz and dx. So write dz and dx plus the last one is tau zx dash. So tau zx plus dou tau zx divided by dou z into dz. I've written dz, the left is dx and dy minus for tau zx. We have dx dy written, write it up, dx dy. Last but not the least, we consider something called as component of body forces, and it is positive. We are taking them to be along the respective positive directions. And for this, we need to write the dimension of all the three components, dx, dy, dz. This is equated to 0. Now, let us simplify it. Okay, I'm going to just multiply them, open the brackets. So sigma x dy dz plus dou sigma x by dou x dx dy dz minus sigma x dy dz plus tau yx dz dx plus dou tau yx by dou y dy dz dx minus tau yx dz dx plus tau zx dx dy plus dou tau zx by dou z dz dx dy minus tau zx dx dy plus x dx dy dz equals 0. I have a component here, I have the same component here, so this and this gets cancelled. Yes, then similarly, see here we have minus tau yx dx dy plus tau yx dx dy. This and this gets cancelled. Then minus tau zx dx dy. This gets cancelled with this. So upon simplification, I am left with dou tau x, the dou sigma x, dou sigma x by dx, dou x dx dy dz plus dou tau yx by dou y dx dy dz. We can rearrange them, nothing wrong. Okay, then plus dou tau zx by dou z dx dy dz thus x dx dy dz equals 0. Now I am going to divide the equation by dx dy dz. I'll be left with dou sigma x by dou x plus dou tau yx by dou y plus dou tau zx by dou z plus capital X equals 0. This is the equation of equilibrium. Yes, we have arrived at the equation of equilibrium by considering summation fx equals 0. Now, if you consider with respect to summation fy equals 0 and then summation fz equals 0, I can just generalize it and write. Okay. So first, while considering summation fx equals 0, we have dou sigma x by dou x plus dou tau yx by dou y plus dou tau zx by dou z plus x equals 0. So similarly, I can write dou tau xy by dou x plus dou sigma y by dou y plus dou tau zy by dou z plus y equals 0 and then dou tau xz by dou x plus dou tau yz by dou y plus dou sigma z by dou z plus z equals 0. This forms equations of equilibrium. We have arrived at all the three equations of equilibrium. Now, if in the problems you will be having numerical problems, in that they are going to give you the equations of stresses and then they are going to tell you to find the equation of equilibriums with respect to some value, or they're going to ask you to find if the given problem is in equilibrium or not. If they give you the value of the body forces x, y, z, then this is the formula that has to be used. If they tell you in the question that the body forces are absent, okay, if the body forces are absent, then what happens to your equations of equilibrium is we are just going to rewrite the same equations, just that this capital X, capital Y, capital Z are going to be removed, or they are going to be 0. So it is going to be dou sigma x by dou x plus dou tau y x by dou y plus dou tau zx by dou z equals 0. Then dou tau xy by dou x plus dou sigma y by dou y plus dou tau zy by dou z equals 0. And then the third is dou tau xz by dou x plus dou tau yz by dou y plus dou sigma z by dou z equals 0. I've just made these three equated to 0. Yes, so this is the equation of equilibrium if the body forces are absent. Alright.